Plate tectonics, development of a theory. Mapping the ocean floor. Scientists began exploring the seafloor in greater detail during the later 1940s. The depth of the ocean floor, an echo sounder to measure the depth of the ocean floor. An echo sounder produces sound waves that travel from a ship to the seafloor. The wave echo or bounce of the seafloor and back to the ship. The echo sounder records the time it takes the echo to return. When the ocean is deeper, the time it takes the echo to return. When the ocean is deeper, the time it takes for the sound waves to bounce back is longer. Scientists calculated ocean depth and used these data to create topographic maps of the seafloor. These new topographic maps show the large mountain ranges that stretched for many miles along the seafloor. The mountain ranges in the middle of the oceans are called mid-ocean ridges. Mid-ocean ridges shown in the figure below are much longer than any mountain range on land. The seafloor spreading. By 1960s, scientists had discovered a new process to help explain continental drift. This process is called seafloor spreading. Seafloor spreading is a process by which a new oceanic crust forms along a mid-ocean ridge and older oceanic crust moves away from the ridge. When the seafloor spreads, Earth's mantle melts and forms magma. The liquid magma is less dense than the solid mantle. The magma rises through the cracks in the crust along the mid-ocean ridge. When magma reaches Earth's surface, it is called lava. As the lava cools and crystallizes on the seafloor, it forms a type of rock called basalt. Oceanic crust is mostly basalt. Because the lava erupts into water, it cools rapidly. The rapidly cooling lava forms rounded structures called pillow lava. As the seafloor spreads apart, new crust that is forming pushes the older crust away from the mid-ocean ridge. The mid-ocean ridge at the center of the formation is shown below. The closer the crust is to the mid-ocean ridge, the younger the oceanic crust is. Scientists concluded that as the seafloor spreads, the continents must be moving. Seafloor spreading is the mechanism that explains Wegener's hypothesis of continental drift. Topography of seafloor. What determines the topography of the ocean floor? One factor is seafloor spreading. The rugged mountains that make up the mid-ocean ridge system can form in two different ways. Some form as large amounts of lava erupt from the center of the ridge. That lava cools and builds up around the ridge. Others form as the lava cools and form new crust and cracks. The rocks move up or down across these cracks and form the jagged mountains. Sediments also determines the topography of the ocean floor. Close to a mid-ocean ridge, the crust is younger and there is no much sediment. However, farther from the ridge, sediments become thick enough to make the seafloor smooth. This deep, smooth part of the ocean, shown below, is called the abyssal plain. Moving continents around. The theory of seafloor spreads provides a way to explain how continents move. Continents do not move through the solid mantle or the seafloor. However, the seafloor spreading suggests that continents move as the seafloor spreads along a mid-ocean ridge. Development of a theory. Just as evidence was needed to support continental drift, evidence was needed to support seafloor spreading. Some of the evidence to support seafloor spreading came from rock on the ocean floor that was not covered with sediments. Scientists studied the magnetic signatures in these rocks. They discovered two important things. First, Earth's magnetic field changes. Second, these changes appear in rocks that are made up in the seafloor. Magnetic reversals. Earth's iron-rich liquid outer core is like a giant magnet that creates Earth's magnetic field. The directions of this magnetic field is not always the same. Today's magnetic field is described as having normal polarity. Normal polarity is the state in which magnetized objects such as compass needles will orient themselves to point north. Sometimes a magnetic reversal occurs and the magnetic field reverses direction. The opposite of normal polarity is reverse polarity. Reverse polarity is a state in which magnetized objects reverse direction and orient themselves to a point north. Sometimes a magnetic reversal occurs and the magnetic field reverses direction. The opposite of the normal polarity is reverse polarity. Reverse polarity is a state in which magnetized objects reverse direction and orient themselves to point north. Magnetic reversals have occurred hundreds of times in Earth's past. They occur every few 100,000 to every few million years. Rocks reveal magnetic signature. Ocean crust contains large amount of basalt. Basalt contains iron-rich minerals that are magnetic. Each mineral acts like a small magnet. The figure below shows how magnetic minerals align themselves with Earth's magnetic field. When lava erupts along the mid-ocean ridge, it cools, crystallizes, and permanently records the direction of Earth's magnetic field at the time of eruption. Scientists have discovered parallel patterns in the magnetic signature of rocks on either side of the mid-ocean ridge. For example, in the clue below, notice the normal pattern that exists closest to either side of the mid-ocean ridge. Likewise, this reversal of polarity pattern exists at the same distance on either side of mid-ocean ridge.